Welcome back, students. In this video segment, we will take a look at section 7.3, trig substitution or trigonometric substitution. We're basically in the middle of chapter 7, and we're looking at learning techniques of integration that can be used in other STEM math courses or for math majors. Okay, so in this section, I think I'll start out with my own example. So here's my example. For example, it's a very easy example to state. The example is find the area of a circle of radius 3. And if you're thinking, oh, just substitute in a equals pi r squared, r equals 3. Well, that's not what I mean. I want us to use calculus to do this. So let me state the problem. Find the area of a circle of radius 3. Radius 3. And I want to use calculus to do that. Well, in order to use calculus to do that, I'm going to need something really big from Calc 1. It says that if you have a function that is non-negative, that means a function that lies above the x-axis, essentially, between 2 points on the x-axis a and b, then the area bounded between the function and the x-axis is the definite integral of the function between a and b. So in order to do this, we're going to need a function, and circles aren't functions. So we'll handle that in a very special way. So let's consider the equation of a circle centered at the origin of radius 3. So x squared plus y squared equals what? 9. Okay, so that's the entire circle. Now if I solve this equation for y, I get y equals plus or minus the square root of 9 minus x squared. And that gives us the upper and lower half of a circle. So I'm going to solve for just the upper half. I'm going to take the positive square root, and that gives me y equals the square root of 9 minus x squared. So this is the upper half of the circle. Upper half. Okay, so let's use that as our non-negative function since it lies above the x-axis. And it's a circle of radius 3, so we could look at this as a function between x equals negative 3 and x equals positive 3. And there's our circle. So the area then by Calc 1 is equal to the integral from negative 3 to positive 3 of the square root of 9 minus x squared. What I think I'm going to do is I'm going to use a little more trickery here. I'm going to just use the quarter of the circle, the first quarter of the circle, the quarter of the circle in the first quadrant, and use that to find the area of the circle. So I'm going to integrate from 0 to 3. Now this gives me the area of 1/4 of the circle. So the first integral I set up, if I multiply it by 2, that gives me the entire area of the circle. Remember, the integral from negative 3 to positive 3 was the area of the upper half of the circle. So if I multiply by 2, I get the lower half included. So I get the total area. So if I change the limits to be between 0 and 3, looking only at the first quarter of the circle, the quarter in the first quadrant, then I would multiply that by 4 to get the entire area. Okay, so our task is to then use the fundamental theorem of calculus to find this area. Well, we have a problem in Calc 1. In Calc 1, we couldn't possibly do this because a U substitution, the only method that we have available to us in Calc 1, would not produce a du. If we made the substitution u equals 9 minus x squared, then du would be negative 2x dx, and that x is a major problem. This is a major problem with the u substitution. So essentially, it's so much of a problem that we can't use u substitution the way we know it to solve this problem. So instead, we're going to use a new method. We're going to use a method of trigonometric substitution. I'm going to make a substitution of a trig function underneath the integral sign that will get rid of that radical. That's the problem. The problem is the radical. So why is the radical the problem? The radical is the problem because of the minus sign. So the minus sign is really the problem. If that minus sign were not there, then we would be able to integrate this. We can't. The problem is the minus sign. So first, I stated the problem is the radical. Well, that is the problem. So to get rid of the radical, it would be nice if the minus wasn't there. So the minus is the problem. So the whole idea is to make some sort of substitution that will eliminate that minus. Remember that the square root of, let's say, a squared minus b squared or plus b squared is not equal to the square root of a squared minus this or plus the square root of b squared. So that's what I was indicating as the problem. So let's see what we can do. Before we make the substitution, let's suppose we had a similar situation. Instead of 9 minus x squared, we had 1 minus x squared. Square root of 1 minus x squared. Okay. So I'd like to make some sort of substitution that would get rid of the minus. Okay, so let's just look at the 1 minus x squared. Let's just look at the expression without the radical. Now, right below that 1 minus x squared, I'm going to write the key to this whole situation. So 1 minus sine squared. What's 1 minus sine squared? It's cosine squared. The minus goes away. So if I had the square root of 1 minus sine squared, I'd have the square root of cosine squared, and I'd no longer have that minus sign. I have another little problem in that you can't just get rid of the square and square root. A lot of students will do that. We have the absolute value involved here. Okay, remember from algebra, this is a big deal from algebra, that the square root of a squared is not a, it's the absolute value of a. Well, we're going to get around that problem. Our substitution is going to be so that when we do get rid of the minus, we're not going to have to worry about the absolute value. It's going to turn out that the absolute, and I'll show you why in a few minutes, that the absolute value will not be necessary. So this will be for us. Okay. Now, if I can make this substitution that indicated in red there, that would eliminate the square root, then I can go ahead and get rid of the square root. I think I just said that. Sorry, I don't like that sentence, but I'm not going to edit it out of the video. I'll just keep it real. Okay, so if in the expression the square root of 1 minus x squared, I let x equal sine theta, then the square root of 1 minus x squared becomes the square root of 1 minus sine squared theta, which is the square root of cosine squared theta, or cosine theta. That's the whole key to our problem. But our problem doesn't have 1 minus x squared. It has 9 minus x squared. So what am I going to let x equal in order to deal with the 9 minus x squared? The 9 and 9 minus x squared. Well, if I make a substitution that will allow me to have 9 minus 9 sine squared, that would give me 9 times 1 minus sine squared. So if I can make a substitution that would give me x squared equal 9 sine squared, then I'll be able to factor out the 9. I'll have 9 times 1 minus sine squared, which is 9 cosine squared, and the minus is gone. So in order to do that, I'm going to need to make the substitution. X equals not 9 sine theta, but 3 sine theta. If I do that, and I want to get rid of this stuff here, if I do that, oops. Oh boy. So if I do that, I'm still getting used to my notepad here. Then I make the substitution 9 minus 9 sine squared theta, which becomes the square root of 9 times 1 minus sine squared theta, or the square root of 9 cosine squared theta, and the radical's gone. 3 absolute value of cosine, but for us we're going to not need the absolute values, and that's the key. That's the key. And then we integrate something to do with cosine theta rather than the original x variable. Okay, so let's do this. Let's evaluate. Let's figure out our area. What I'm going to do is I'm just going to consider the antiderivative rather than the definite integral. I'm going to take the limits of integration out and just look at this as an indefinite integral. Then I'll put the limits of integration from 0 to 3 back in. Okay, since the whole idea is to practice with anti-differentiation. So, okay, so I'm going to let x equal 3 sine theta, and look at the red arrow up there. So if I do that, I'm going to get all that algebra I did above. I'm going to get the square root of 9 minus 9 sine squared. But there's a problem. There's a problem that goes right in the integral, right there, right in that red area, in the red arrow. I'm going to need the differential, and I can't put dx there because the new variable is theta. So back up to our substitution. Let x equal 3 sine theta. I'm going to need dx then, which is 3 cosine of theta d theta. And that goes in the position where my little red arrow is. So what I'm going to do is I'm going to put dx is 3 cosine theta d theta, and then I go forward. All the algebra I did says that radical turns out to be 3 cosine theta times the 3 cosine theta d theta from the differential, which means I'm looking at 9 times the integral cosine squared theta. And this puts us squarely in section 7.2. In section 7.2, we look at powers of trig functions. And this is the case where we're dealing with even powers of sines and cosines. So I'm going to do what's standard in that section. I'm going to use a power reducing formula for cosine squared, sorry. Okay, so cosine squared equals 1/2 times 1 plus cosine of 2 theta. So this is 9/2. 1/2 can be factored out. It's constant. Integral of 1 is theta. Integral of cosine of 2 theta is 1/2 sine 2 theta. And all this plus a constant. Now notice a couple of things. First, I've said it a few times, but this substitution eliminates the radical by eliminating the minus, and later on also pluses underneath the radical. And it leaves our integral in terms of theta, so we have work to do. This is not possibly the antiderivative because our variable is not theta, it's x. You can't leave your answer in terms of a variable we never even started out with. So we have a little work to do. So let's go back to our substitution. X, the substitution was x equals 3 sine theta. Well, that says that sine of theta equals x over 3. And that says that as long as we choose, and this is where the absolute values of the cosine, the absolute values are not necessary in the substitution. This is the reason. We're choosing theta so that the inverse sine of theta exists. If you missed that, I'll say it again. My antiderivative above needs theta. That means I'm going to need to solve for theta. That means I'm going to need the inverse sine function. That means that I'm going to have to restrict theta to be between minus pi over 2 and pi over 2. If theta is between minus pi over 2 and pi over 2, then the inverse sine exists and I can solve for theta. Now, back to the substitution. Back to the substitution. Remember, look at the new red arrow, square root of 9 cosine squared theta, and somehow the absolute value, which should go there, doesn't go there. Well, we're choosing theta so that the inverse sine exists, not the inverse cosine, but the inverse sine. That means theta is between negative pi over 2 and pi over 2. That means theta is either in quadrant 1 or quadrant 4 in standard position if you graphed it. In quadrants 1 and quadrants 1 and 4, the cosine is positive, so we eliminate the absolute values. You don't have to obsess over that detail. What you remember is that each time we make these substitutions in this section, you don't have to worry about the absolute value for a change. Usually it was a real big problem, like in algebra, pre-calculus, and trig. It was really a problem to keep track of the absolute values. So we don't have to worry about them here. Okay. Well, we're almost set to write out our solution, our antiderivative at least. We have one more little problem. Little problem, which I think I'll highlight in green. Little problem is I have in my antiderivative the sine of 2 theta. And my trig substitution says the sine of 1 theta is x over 3. So we get a little bit of a problem. So let's go back to our antiderivative. Our antiderivative has sine of 2 theta in it. Now, the sine of 2 theta is equal to 2 times the sine of theta times the cosine of theta. You really must know this. This is the only double angle formula for sine. So our antiderivative, the square root of 9 minus x squared dx, then is 9 halves theta plus sine of theta times cosine of theta plus a constant. Okay, well, what happened to the 2 in the 2 sine theta, cosine theta? Well, the antiderivative has 1/2 sine of 2 theta. So that 1/2 cancels with the 2 from the double angle formula. And we still have one more little problem. Our trig substitution says sine of theta equals x over 3, and our antiderivative also has cosine of theta in it. Well, we handle this in a way that's going to become second nature to you because it happens all the time in this section. What we do with our substitution is we draw a little right triangle, and we consider the substitution as giving us the parts of the triangle. The opposite of theta is x, the hypotenuse is 3. Remember, sine is opposite over hypotenuse. The Pythagorean theorem will give you that remaining side as 9 minus x squared. If you're not sure about that 9 minus x squared in the third side, then you ought to stop the video use the Pythagorean theorem and convince yourself that it's true. The square root of 9 minus x squared is by the Pythagorean, I'll abbreviate it, theorem. Okay? All right. So back to our antiderivative. We're almost there. This goes much more smoothly in practice. We're just learning this for the first time, so it goes real slow, but it goes very smoothly in practice. Theta was the inverse sine of x over 3. X over 3. The sine of theta was x over 3. That's our substitution. So plus x over 3. The cosine of theta, look at our triangle, is adjacent over hypotenuse plus a constant. Okay. This is the main point of the problem. I want to finish the problem so that we have an answer, but this is the main point here. So our area equals the integral from 0 to 3 multiplied by 4, so we get all four quadrants, or all four quarters of the circle. Integral 9 minus x squared dx. Our antiderivative is right above, so it's 4 times 9 halves, or 18. Make sure 4 times 9 halves is 18. Yeah. Times the inverse sine of x over 3 plus x times the square root of 9 minus x squared over 9. Remember, this is a definite integral now, carried between 0 and 4. Oops, not 0 and 4, 0 and 3. Let's see here. Okay, so let's get this done. So this is the constant 18, and I'm going to substitute the upper limit of integration. So this is the inverse sine of 3 over 3, which is 1. If I substitute x equals 3 into the second part of the second term in this antiderivative, I get 0. Now, if I substitute the bottom limit, the lower limit of integration, I have the inverse sine of 0, which is 0 in the first term. In the second term, I also have a factor of x in that, and just before the radical, so substituting 0, I get 0. This is the only thing I have left. I have 18 times the inverse sine of 1. What's the inverse sine of 1? Remember, inverse trig functions give you angles. So when the sine equals 1, what the angle gives you is pi over 2, or gives pi over 2. 18 times pi over 2 is 9 pi. Square units. Square units. Real easy to check here. What's the area of a circle? Area of a circle is pi r squared. What's the area of our circle? 3. Pi times 3 squared, 9 pi. Checks out nicely. Checks out nicely. Okay. Let's not get too lost in this geometry and area. The big problem was to find the antiderivative of 9 minus x squared. And the key is to make a trig substitution. X equals 3 sine theta, which eliminates the radical. And in eliminating the radical, we transform our trig function, our antiderivative, to trig functions, sometimes powers of trig functions, etc. And we proceed forward. Okay, so for the remainder of this section, I'm going to look at different cases that could happen, and we'll look at examples of each case. Okay. So what we just did is we handled a rather large case. Let's say we'll call it case 1. Case 1, the integral has the square root of a squared minus x squared in the function. Okay, so the substitution is x equals a sine theta. We also then have dx equals a cosine theta d theta. And that substitution will completely eliminate the problem. The problem was, or is, the minus sign. So if I make that substitution, underneath the radical sign becomes this, a squared times the quantity 1 minus sine squared, which is a squared cosine squared, the square root of which is a cosine theta. So this is what happens each time we make this substitution in the case 1. All right. So now let's look at, before we look at the other cases, and there are only 2 other cases. Let's take a look at one more example of case 1. Okay. The example then is evaluate the integral 1 over the quantity x squared times the square root of 16 minus x squared. So in our integrand, we have the square root of 16 minus x squared. So the substitution then will be x equal what? It will be 16 sine? No, it will be 4 sine theta. So then dx equals 4 cosine of theta d theta. Then we make the substitution. We're looking at 1 over x, 4 sine theta, squared, square root of 16 minus x squared, 4 sine theta squared. Not dx now. Dx is replaced with 4 cosine theta d theta. So don't just replace the d theta with d, or the dx with d theta. We have to replace dx with whatever the substitution tells us dx is. Okay, so let's go ahead and simplify. This becomes 1 over 16 sine squared times the square root of 16 minus 16 sine squared times 4 cosine theta d theta. Let's simplify. In the numerator, I can put the 4 cosine theta d theta. In the denominator, I'm looking at 16 sine squared theta. 16 minus 16 sine squared is 16 cosine squared. And simplify some more. 4 cosine theta d theta in numerator. The square root of 16 cosine squared theta is 4 cosine theta. Okay. And the 4 cosine theta cancels out. From the numerator and denominator, the 16 can be brought out as 1/16. We're looking at 1 over sine squared d theta. Now, how do we integrate 1 over sine squared? 1 over sine squared. 1 over sine squared. Well, what is 1 over sine squared from trig? It's cosecant squared. So now we have to remember back from Calc 1. What's the integral of cosecant squared? Well, off to the side here, the integral of secant squared is what? You should know this by now. If not, I'll tell you, but you should know this. integral of secant squared is tangent plus a constant. So the similar form would be cosecant squared. The integral of cosecant squared then would be minus cotangent of theta plus a constant. Okay, so we're going to use that. That's from Calc 1 again. So we're going to get negative 1/16 cotangent of theta plus a constant. How do we go from here? Or can this possibly be the answer? No, can't possibly be the answer. Our original integral was in terms of x, so we have to have our solution also in terms of x. But remember, the substitution was x equals, I forgot, 4 sine theta. 4 sine of theta. So that says that sine of theta equals x over 4. So how can we go from sine of theta equals x over 4 to cotangent of theta? Well, we do that the same way we did in our introductory example. We draw a little right triangle, put the angle theta in the lower left-hand corner. Sine is opposite over hypotenuse. The Pythagorean theorem will give you 16 minus x squared for the remaining sine. By the way, in these little triangles, the remaining side is always the square root that was in the original problem. Notice in the original problem, we had the square root of 16 minus x squared. And look at what happens in the little triangle that we draw to help us finish the problem. It's the same. There are very few always answers that I give, and this is one of them. This always happens. This always happens. It always happens that the remaining side is the radical that's underneath the square root sign, or in the integral, provided it is square root and not cube root or seventh root or any other root. So, okay, so we have cotangent. Well, tangent is opposite over adjacent. So cotangent's 1 over that. Cotangent would be adjacent square root of 16 minus x squared over opposite. We could do a little here to clean this up, not much. This is the square root of 16 minus x squared over 16x plus a constant, and that's our antiderivative. That is the antiderivative of 1 over x squared times the square root of 16 minus x squared in the denominator. If you were to look at this in Calc 1 into your future, this would be completely unrecognizable to you. We are now able to evaluate a whole bunch more integrals, even up to these first 3 sections in Chapter 7 than you probably ever dreamt of. Okay? Okay. So, we looked at Case 1. Case 1 involves integrals that have the square root of a squared minus x squared in the integrand. I called that Case 1. Case 2, our next case, is the integrand contains a squared plus x squared. Okay. Now remember, in Case 1, I wanted to use or make a substitution. The substitution I created was based on the idea that 1 minus sine squared equals cosine squared. And this allowed us to get rid of the minus. Well, where's an identity from trig? What is an identity from trig? A similar one that gets rid of plus, or changes the plus on the left side to no more plus. So 1 plus what is something squared? 1 plus tangent squared is secant squared. Well, the original substitution in Case 1 was motivated by 1 minus sine squared to give us x equals a sine theta. So what do you suppose the identity 1 plus tangent squared is gonna motivate us for the substitution? That didn't come out very well. What do you think the substitution would be then corresponding for a squared plus x squared? A tangent theta. Okay, and that's the substitution that we make. This is the substitution. So let's take a look at a specific example. Let's take a look at the example. Evaluate the integral of x squared over the square root of 25 plus x squared with respect to x, so dx. Calc 1 to do this, not going to happen. In Calc 1, can you see what would be the problem if we made u equal to 25 minus x squared? What's the problem in the numerator? The problem in the numerator is that the power's too high. In order to make the substitution u equals 25 minus x squared, we need du to have x dx in it, and not x squared dx. So the power would need to be to the first power in the numerator. Okay? So let's make the substitution. Let's let x equal a 5 tangent theta. So dx equals 5. The derivative of tangent is secant squared. And then we make our substitution. So in the numerator, it looks like I'm going to have 25 tangent squared theta, because I'm letting x equal 5 tangent. In the denominator, I'm going to have 25 plus 25 tangent squared theta. Now, do I just write d theta? No. Because dx is not just d theta. dx is 5 secant squared theta. D theta. So now we've transformed our integral from x's into thetas. Let's simplify the integrand. We're looking at 25 tangent squared theta. In the denominator, 25 plus 25 tangent squared is 25 secant squared times 5 secant squared theta d theta. In the denominator, I have 25 secant squared now, which is 5 secant theta. And dx is 5 secant squared theta d theta. Well, we don't get that nice cancellation of the denominator yet, or rather in this problem like we did in the previous problem. The 5 cancels. The 25 can be brought out front as a coefficient, but we're left with tangent squared times secant. And this is significant. This is a significant problem. Do you remember how to deal with this? This is from 7.2. Well, the key, this was the last case in powers of tangent and secant. The key is to write tangent squared as secant squared minus 1. So this is the unpleasant case. Reduced to powers of secant. And that leaves us with 25 times the integral of secant cubed minus secant. And these are significant integrals. These are not trivial integrals. But we did the work for secant cubed, and we memorized the integral from secant. Okay, so I'm going to borrow our stuff, or borrow our antiderivatives from Calc 1, from 7.2. So in 7.2, and if you need to stop the video to remind yourself of how to integrate secant cubed, that's fine. Feel free. In 7.2, though, we ended up with the integral of secant cubed is 1/2 secant tangent plus the natural log of secant plus tangent. Okay, and the integral of secant we memorize as minus, well, only minus because of the negative there, but it's the integral of secant is the log of secant plus tangent. Again, if you're not if this isn't ringing a bell for you, you ought to stop the video and remind yourself how to integrate secant cubed. Okay, don't let this go. This is going to be very significant coming up, that you remember how to do this stuff. Okay, so plus a constant. Then we do our transition from trig back to powers of x, or not powers of x, but functions of x. Okay, so I'm going to first simplify this a little bit before we go back to the variable x. I'm going to have 1/2 secant theta tangent theta. Now if I distribute that 1/2 to the logarithm, I'm going to have 1/2 log of secant plus tangent in absolute values. And then I'm subtracting log of secant plus tangent. So what that's going to leave us with is minus 1/2 times the log of secant plus tangent. Okay, all of that plus a constant. Now what I think I'll do is I'll factor out the 1/2, because we have a little bit of work to do here. Factor the 1/2 out from the whole inside of the brackets. Secant theta plus tangent theta to finish out the stuff inside the brackets. Now we do the task, go through the task of converting to x, which means that we draw our little triangle. We draw our little triangle somewhere on our page, right triangle, with our substitution. The substitution was x equals 5 tangent theta. The substitution was 5 tangent theta. So let's come down, back down to our little triangle. X was 5 tangent theta. So that says tangent theta is x over 5. Tangent is opposite over adjacent. Pythagorean theorem will give us the square root of 25 plus x squared. No coincidence that square root of 25 plus x squared is what's underneath our integral sign to begin with. This always happens. Okay, so let's get this done here. So this is 25 over 2 secant theta times tangent theta. Well, secant's 1 over cosine, and cosine is adjacent over hypotenuse. So secant theta will be hypotenuse over adjacent. Square root of 25 plus x squared over 5. Tangent theta was the substitution, or you could take it right off your triangle. X over 5. Minus the natural log of secant, again, the square root of 25 plus x squared over 5, plus tangent x over 5, plus a constant. I'm going to clean this up just a little bit. This is 1/2 x times the square root of 25 minus x squared, plus x squared. And I got that by distributing the 25 over 2 back in. Minus 25 over 2 times the natural log of square root of 25 plus x squared plus x over 5, all this plus a constant. Okay, well, this is fine. In fact, I would expect it on homework and on your exams and stuff, you would just leave it like this. This is not how it's going to be written in the textbook. The author is likely, almost 100% likely, to write it like this. The first term, same. But it's very likely that you're going to see the last term without that over 5 within the logarithm. How in the world can that be? How in the world can that be? These are not the same expressions, not the same logarithmic expressions. You have over 5, you have something over 5, you take the logarithm and you have the over 5 is gone. Well, you don't have to do this with your answer. What your author used is this, and this is very commonly done. The logarithm of a over b equals the logarithm of a minus the logarithm of b. So that logarithm with the 5 in the denominator, which again, you just leave it like that in your homework. It's fine. Or on your exam. There's no need to do what your author does, even though it's very, very common. So in the original, our answer looks like this. Just that logarithm can be written as the natural logarithm of the square root of 25 using the algebra property that I just wrote above this, plus x minus the log of 5. Now that minus log of 5 is just a constant, which can be absorbed into the constant of integration, just added into the constant of integration. That's about the shortest explanation I can give. But you can write, you don't have to worry about that. You can write your solution just like I'm highlighting in red with the 5 in the underneath the radicals within the logarithm, and that's just fine. Okay. So we have one more case to look at. Let's look at case 3. And the example is to evaluate our last integral for this section. Integral of x squared over the square root of x squared minus 5. And this will take us to case 3. So just to remind you, case 1, if our integral contains the square root of a squared minus x squared, a squared is constant, then the substitution is a sine theta. Case 2, the integral contains the square root of a squared plus x squared. Let x equal a tangent theta. Our last case, and our example above is an example of our last case. Not a squared minus x squared, that was our first case, but x squared minus a squared, so the variable comes in first. Well, the substitution is going to be x equals a secant theta. The short reason for that is that secant squared theta minus 1 is tangent squared theta. So if I substitute a secant theta, the minus will disappear under the radical sign, and hopefully we have an easier situation to deal with than we had to start. So back to our integral. Our integral is integral of x squared over the square root of x squared minus 5, and that x squared minus 5 needs to be x squared, represent our x squared minus a squared. So that means that the 5 is our a squared. So what's a? Even more specifically, what's our substitution? Well, it's definitely x squared minus a squared as a case, and a equals what? It's the square root of 5 secant theta. So sometimes we need to have square roots in our substitutions. So dx equals the square root of 5, and what's the derivative of secant? It's secant theta times tangent theta d theta. Let's make the substitution. So our integral then becomes the square root of, our integral rather, is the integral of x squared over x squared minus 5, square root of, and that becomes, well, x is radical 5 secant theta, so x squared is 25 secant squared theta. In the denominator we have the square root of x squared, 25 secant squared. Oh my goodness, that's not right. In the numerator or the denominator. If x equals radical 5 secant, x squared is not 25 secant, it's just 5 secant. This is an easy fix. And the denominator as well. So, sorry about that. In the denominator we have x squared 5 secant squared theta minus 5. Dx is radical 5 secant theta tangent theta. Don't forget, you don't just replace dx with d theta. In this case, dx equals radical 5 secant theta tangent theta. Okay, so let's simplify our integrand. So this is 5 secant squared theta over 5 secant squared theta minus 5 is 5 tangent theta, tangent squared theta. So radical 5 tangent squared theta. And the same radical 5 secant theta tangent theta. And the radical in the denominator, the whole reason for this substitution. Radical in the denominator goes away. We have radical 5 then tangent theta times radical 5 secant theta tangent theta d theta, and we can do a lot of cancellation here before we finish this thing off. Okay, so the cancellation is the radical 5's cancel, the tangent cancels, and we combine, we multiply the secant squared times secant to get 5 secant cubed theta d theta, back to the same power of secant that we saw in a previous example. Again, if you need practice with integrating secant cubes, stop the video and do it. I did it for you in video. I think your author also does it in the textbook. In fact, he does integrate secant cubed. I'm looking for it. He integrates secant cubed on page 528 at the bottom of the page, example 8. So if you don't want to dig out the video lecture, you can definitely look at it as an example done in the textbook. So 5 secant, 5 times 1/2 secant theta tangent theta plus the natural log of the absolute value of secant theta plus tangent theta plus a constant. And then we go to the variable x. Once again, we draw our little triangle off to the side, a little right triangle, theta, and we fill in the sides using our substitution. X equals radical 5 secant theta. So secant of theta equals x over the square root of 5. I do better with sines and cosines. So this says cosine equals radical 5 over x. Remember, cosine is the reciprocal of secant. Back to the triangle. Cosine is adjacent over hypotenuse. Pythagorean theorem will leave you with the square root of x squared minus 5. If you're not sure about that, stop the video and use the Pythagorean theorem to get that last side. And we finish off our problem. So this is 5/2 times secant of theta is x over radical 5, just from our substitution. The tangent of theta is opposite over adjacent plus the natural log of that same secant in absolute value plus the tangent or square root of 5 plus a constant. Clean it up a little bit. I can write this as 1/2 x times the square root of x squared minus 5, and that involves distributing that 5/2 back in, plus 5/2 times the natural log of x plus the square root of x squared minus 5 over radical 5 plus a constant. And that's our integral. Okay? And that actually ends this section. So this ends section 7.3. Feel free to dig into homework as soon as you can. And I'm looking forward to talking with you all again soon.